Your brain runs on roughly 20 watts. A modern GPU needs over 300 watts to do the same. So, what is the brain doing differently? This video is about spiking neural networks, a type of AI that speaks the brain's own language. We'll cover 5 topics, starting with the neuron itself. A traditional artificial neuron is simple. Take inputs, multiply by weights, apply an activation, output a number. It outputs a continuous value, like 0.73, and it does this once, instantly, every time data passes through. A spiking neuron works completely differently. It has a membrane potential, a kind of internal charge that builds up over time. Watch the curve. Each time an input arrives, the voltage jumps up. Between inputs, it slowly leaks back down. When it crosses the threshold, it fires a spike, then resets to 0. This is called integrate, leak, fire, reset. The dashed line is the threshold, set at 1.0 here. The leak time constant, tau, controls how fast the voltage decays. A larger tau means the neuron has a longer memory. Stronger inputs produce more spikes, more often. Weaker inputs produce fewer. A real neuron doesn't say a number. Now, how does an SNN process an image like this handwritten digit? A CNN does it in one shot. One forward pass, one continuous output. An SNN does it differently. The same image is presented repeatedly, t times in a row. Here, t equals 4. Each repetition is called a time step. At each step, every neuron decides independently, fire or not fire? The output is a sequence of zeros and ones, not a single number. Bright pixels fire often, dim pixels fire rarely. A bright pixel fires 3 out of 4 steps. A dim pixel fires only once. The firing rate approximates the pixel brightness. This is called rate coding. Now let's zoom out and see the full network. Each circle is one LIF neuron. The network has 4 layers, input, 2 hidden layers, and an output layer. Every neuron in one layer connects to every neuron in the next. At each time step, spikes travel from left to right. The bright input neurons fire first, activating neurons in hidden layer 1, then layer 2, then the output. After all 4 time steps, we look at the output layer. The neuron for digit 1 fired the most, 3 times out of 4. That is the network's prediction. Whichever output neuron accumulated the most spikes wins. This is called spike rate decoding. So far so good. But how do we actually train this network? Here is the problem. The spike firing rule is a step function. Its gradient is 0 almost everywhere, and infinite at the threshold. Backpropagation needs a gradient at every point. A gradient of 0 means no learning signal gets through. The network cannot learn. The solution is the surrogate gradient. The real step function is used in the forward pass. A smooth sigmoid is used only during backpropagation. Its gradient is a clean bell curve, non-zero everywhere near the threshold. The forward pass fires real spikes. The backward pass pretends the function was smooth all along. Spiking jelly handles all of this automatically. So why does any of this matter? In a CNN, every neuron computes on every forward pass. In an SNN, a neuron only does work when it fires. Most neurons stay silent, so most multiplications never happen. The result, an SNN can use just 5 to 10% of the energy a CNN needs for the same task. Neuromorphic chips like Intel Loihi 2 and IBM TrueNorth are designed specifically to run SNNs, consuming milliwatts instead of hundreds of watts. Event cameras, edge AI wearables, and robotic control systems all benefit from spike-based processing. Low power, low latency, always on. LIF neurons. Time steps. Network structure. Surrogate gradients. Energy efficiency. Spiking neural networks, closer to how the brain actually works. Thanks for watching. If this helped you understand SNNs, consider sharing it with someone curious about AI.